All right, so today I'm gonna just resume where I left off from the last review. So the last review I ended by talking about basis and dimension. And I did a couple of examples about verifying that you have a basis for a given space. I'll do one more example of that sort, and then I'm also going to talk about dimension, which I wasn't able to get to last time. First, let's just recall the definition of a basis. So a basis for a vector space V is a set of vectors in V that span all of V and also is linearly independent. Okay? So essentially, you can just think of a basis as a set of vectors which span the whole space and is also linearly independent. And then let's just recall if you have some vectors v1, let's say v1 through vk. So let's say these are vectors in V. Okay. And then remember to be linearly independent. You can say the vectors are linearly independent if the only solution to this equation, let me put arrows on top to emphasize they are vectors. So if the only solution to this equation where you have a combination set equal to 0 is the trivial solution where all the coefficients are equal to 0. Okay. And then remember that what it means to span all of V, that would mean that any vector in V is a linear combination of the given vectors. So you can just say they span all of V if for any vector B in V, there exists a solution to the equation C1V1 plus etc. Equal to B. Okay, because then to say that there's a solution to this equation would be to say that B is a linear combination of the vectors V1 through Vk. Okay, so I just want to do one example, just checking whether a given set of vectors in a vector space is a basis. I'll do an example with polynomials because I didn't do one with polynomials last time. Okay, so let's remember that P2 represents the vector space of all polynomials of degree less than or equal to 2. And then let's say we have 3 polynomials. Say the first polynomial P1 is x squared minus 3x plus 1. Say the second polynomial P2 is 2x squared minus 2x minus 2. And give me 1 second. Something's not right. Well, okay. It's having a small technical difficulty, but maybe it's not an issue. Okay. Sorry, just trying to see if I could fix something, but I'm not sure. But maybe it's not an issue. Okay. So let me just continue. So we had the third polynomial, P3. Let's say this polynomial is 2x plus 1. So these are all polynomials of degree less than or equal to 2. So they're all vectors in the vector space P2. And we want to ask, do these three polynomials, do they form a basis for P2? Okay. So to check if these three polynomials form a basis, so remember a basis has to satisfy the two conditions of being independent and also spanning the space. So we'll start by checking if these three polynomials are linearly independent. Okay. Okay. So to do that, I'm just going to form a linear combination of the polynomials. So I have C1 times P1 plus C2 times P2 and plus C3 times P3. And here, when you're checking for linear independence, you want to set that combination equal to your zero vector. So in P2, the zero vector would be the zero polynomial. And here to kind of emphasize it being the zero polynomial over here, I'm going to write it as 0x squared plus 0x plus 0. Okay. Now for polynomials, the way that you want to work with them is here on the left-hand side. What we're going to do is we're going to distribute the coefficients, and then we're going to group together like powers of x. Okay. So we're going to distribute the c's and group together all the x squared terms. We'll group together all the terms within x, and then we'll group together all of the constant terms as well. Okay, so if we distribute the coefficients, we get a c1 x squared, and we get a 2c2 x squared, and then we have nothing with c3. Okay. If we distribute the c1, we also get a minus 3c1x. We also get a minus 2c2x. And then we'll get a plus 2c3x as well. Okay. And finally, just looking at all the constant terms that you get, so you get a c1 minus 2c2 and plus c3. Okay. All right, so we just rearranged everything, and now we have this polynomial which needs to be equal to the zero polynomial. So here the idea is for these two sides to be equal to each other, the coefficients of x squared have to be equal. So we get c1 plus 2c2 would have to be equal to 0. Next, the coefficient of x on the left has to equal the coefficient of x on the right. So we get minus 3c1 minus 2c2 plus 2c3. That must also be equal to 0. And then lastly, this constant term on the left has to equal this constant term on the right. So we also get C1 minus 2C2 plus C3 equals 0. Okay. So when you apply the definition of linear independence to the problem, you're able to convert that equation into a system of equations. And now we just want to try to solve this system for C1, C2, and C3. So to solve the system, we'll set up our augmented matrix. Now here, the right-hand side is all zeros. Okay. And we're going to be doing row operations to at least reduce it to like at least an upper triangular form. Okay. Here, since the right-hand side is all zeros, it's not too important to be writing down. So I'm just going to save myself a little bit of writing and just ignore the last column because I know it's just going to be all zeros in the end. Okay. All right, so let's start reducing to upper triangular form. So let's do row 2 plus 3, row 1, and we'll do row 3 minus row 1. Okay. And then doing row 2 plus 3, row 1, so it's going to be negative 2 plus 6, 2 plus 0. And then here we're going to get negative 2 minus 2, and 1 minus 0. Okay. So if we just maybe do one more operation to eliminate this negative 4, we can do row 3 plus row 2. And now we have it in the upper triangular form. Okay. So this is good enough for solving the system of equations. So you can see in the last row gives us the equation 3c3 equals 0. So therefore you get that c3 is 0. Then the second row gives you 4c2 plus 2c3 equals 0. And with c3 being equal to 0, you can get that c2 is 0 as well. And finally, the first row gives you c1 plus c2 is 0. And since c2 is 0, you get that c1 is 0 as well. Okay. So here we found that the only solution to the system is where all the c's are equal to 0. So by definition, that means that our 3 polynomials were linearly independent. Okay. Okay. Now that's technically not enough to show that it's a basis because remember, to be a basis, it has to be both linearly independent, but it also has to span the space. So we've only checked for linear independence. What we need to do now then is check to see, do these 3 polynomials span all of P2? Okay. Now remember that for span, what you're doing is you're taking a linear combination of your given vectors and you're setting it equal to like an arbitrary element of your space. So here, to check for span, it would be set up in a similar way, where you'd form a combination of the 3 polynomials. Okay, but whereas for independence, we set it equal to 0. For span, we set it equal to like a generic element of your space. So here, sort of generic polynomial degree less than or equal to 2 will look something like this. Okay. So then what it means to span, it just means that there is a solution to this equation. Okay. So we're just checking to see if there's a solution to this equation no matter what A, B, and C are on the right. Now, here you can convert it into the same system of equations that we have here. Let's see here. Only difference is, again, instead of the right-hand side all being equal to 0, when we set the, so when we do the step where we combine like powers of x on the left, it would be set equal to ax squared plus bx plus c when we're checking for span. So you get c1 plus 2c2 equals a instead of 0, because now a is the coefficient of x squared. Likewise, you'd get this portion equal to b, because now b is the coefficient of x. Likewise, this part would be equal to c now. Okay. So then when you set up the augmented matrix and you start trying to see is there a solution, okay. Now we've already reduced the left-hand side to this upper triangular form. And you'll get some stuff on the right, but it's not too important. Okay. Here at this point, though, you see that you would be able to solve the system for C1, C2, C3 by doing back substitution. Similar to how we did for linear independence. Okay. So the fact that there is a solution to this system of equations, no matter what we have on the right, that proves that our three polynomials also span P2. Okay. Remember, for span, you just need for there to be a solution. And here we can see that there will be a solution, which you could get if you did back substitution. Okay. So then we have these three polynomials will also span P2. And so now, since we know that they are linearly independent and they also span, we can conclude that these three polynomials, in fact, form a basis for P2. Okay. All right. Okay, and then I talked about it last time, so I'm just going to very quickly mention it again. Okay, so when you're checking for linear independence, and you know, from the definition of independence, you get your system of equations, and then from there you get your coefficient matrix. So last time I talked about how to be independent, you have to have a pivot in every column, which we do in this example. Yeah. And then if you have a column that's missing a pivot, that would introduce a free variable in the system. And if you have a free variable, you'll have infinitely many solutions, which would disprove independence, because independence says there's only one solution, which is that all the coefficients are 0. Okay. So this is kind of like it's kind of a simple way of maybe thinking about these types of problems. To check for independence, you just want to have a pivot in every column. Now, as for span, so remember that for span, you just need there to be a solution. So the only time there wouldn't be a solution, at least not always, so maybe let's write it like this. So a solution will not always exist when you get a row of zeros, when you're doing your row operations. So when you get something like this, so then this would be an indication that it doesn't span, or that your vectors don't span your space, to be more precise. Okay. So kind of a simple sort of shortcut way of thinking about it would be that for your vectors to span the space, you'd have to have no rows of zeros when you do your row operations. Or if you will, you can think about it saying there would have to be a pivot in every row to span, okay? All right. But that's kind of all I wanted to do for the first part. Just one more example of checking if a given set of vectors is a basis or not. Let me now talk about dimension a bit, okay? So the dimension of a vector space is defined to be the number of vectors in any basis for the space. Okay. So as an example, in the last example, we just found a basis for P2 that we found has 3 polynomials in it. Okay. So therefore, the dimension of P2 would be equal to 3. Okay. Now, it is a fact that for any vector space, the number of vectors in any basis for that space is always the same. So like for P2, every basis for P2 will have 3 polynomials in it, and its dimension would be 3 by definition, okay? Okay, so let's just maybe look at some other sort of like common examples of vector spaces that we work with in this class. And let's maybe see what their dimension is, okay? Okay, so the dimension of Rn as a vector space would be equal to n. So that's maybe intuitive. We've always been thinking of R2 as being like two-dimensional, R3 as being three-dimensional. But formally, with this definition of dimension, you can say that dimension of Rn is equal to n. And maybe just like as an example, in R3, these three vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, these three vectors form a basis for R3. They call this the standard basis. And similarly in Rn, if you take the vectors that have like 1 and 1 entry and 0 everywhere else, or if you will, these are just like the columns of the identity matrix, if you will, these vectors will form a basis. So there would be n vectors in this basis, so therefore the dimension of Rn is equal to n. For the dimension of the space of all m by n matrices, the dimension is going to be m times n. So just like kind of as an example to see why that would be the case, let's do, okay. So let's look at a specific example, M 2 by 3, so the space of all 2 by 3 matrices. So a 2 by 3 matrix looks something like this. And here, let me just kind of real quickly rewrite this generic 2 by 3 matrix as a linear combination. So I'm sure you guys can see how I'm getting this. Okay. But yeah, so any 2 by 3 matrix can be expressed as a linear combination of these 6 matrices where you have a 1 and 1 entry and a 0 everywhere else. Okay. So the fact that any matrix in M2 by 3 as a linear combination of these 6 matrices, that shows us that these 6 matrices span M2 by 3. And then if you were to try to check if they were independent or not, so for linear independence, you would set this combination equal to 0. But when you set this equal to 0, if you set this equal to 0, you would immediately get that A is 0, B is 0, and so forth. So that you would see that these matrices also satisfy the definition of being linearly independent. So they would form a basis for M2 by 3. So since you have 6 elements in this basis, the dimension is going to be equal to 6. Okay. And you can kind of generalize this argument for any m by n. So like for any vector space of like m by n matrices, if you take the matrices that have a 1 and 1 entry and 0 everywhere else, those matrices would be a basis for the space. You'd have m times n such matrices, so the dimension is therefore n by n, okay? Lastly, for the dimension of space of polynomials, the degree less than or equal to n. So the dimension of Pn is n plus 1. So let's just say, like as an example, if we look at the space of polynomials, a degree less than or equal to 3. So such polynomials would look something like this in general. And here, this is kind of already naturally a linear combination of the polynomials x cubed, x squared, x, and then we have the constant polynomial 1. Okay. So these 4 polynomials, they span P3. They're also going to be linearly independent, so they form a basis for P3, and since you have 4 polynomials in this basis, therefore the dimension of P3 would be equal to 4. Okay. And then you can generalize this for any n, so dimension of Pn would be n plus 1 in general. Okay. Now I'll say one more thing about dimension, and then I'll move on to a new topic. So let's say that we have an n-dimensional space. Okay. So if, let's say that we also have n vectors v1 through vn. These are vectors in our n-dimensional space V. There's a theorem that says that if these n vectors are linearly independent, then they also span V and therefore would form a basis for V. Okay. Okay, so what this theorem is saying is if you have n vectors in an n-dimensional space, okay, so it's important that those numbers match up, n vectors in an n-dimensional space, then it's enough to just check if those n vectors are linearly independent to check if they're a basis or not. Because if they are independent, you'll kind of get, like, as a freebie, that they also span the space and would therefore in fact be a basis. Okay. Okay. Likewise, if you have n vectors in an n-dimensional space that span the space, so if I, instead of linear independent, if I say that they span, then they would also be linearly independent and therefore be a basis. Okay. So really, when you have n vectors in an n-dimensional space, you only need to check one of the conditions of being independent or spanning. And once you verify one of them, the other is guaranteed to also be true. Okay. And therefore, you'll know that you have a basis. All right. So kind of as an example, let me go up to the first example that we did. Okay, so we had 3 polynomials in P2. So if we knew that the dimension of P2 was equal to 3 ahead of time, then what we could have done is we could have just checked for independence in this first part, and then we could have skipped checking for span as we did down here. And at this point, we could just say, since P2 is three-dimensional, and we have 3 polynomials which are linearly independent, it follows that they form a basis for P2. Maybe I'll put it in a set this time. So we could have concluded that they were a basis without checking for span. If we knew that the dimension of P2 was 3, and we had 3 independent polynomials, then they would have to be a basis, and you wouldn't have to check for span. Okay? Okay. All right, so now for the remainder of the review, I'm going to talk about the 4 fundamental subspaces of a matrix. So we've already seen 2 of them. We have the null space, which we denote as n of a. So remember that the null space was the space of all solutions to the equation ax equals 0. So to find the null space of a matrix, it amounts to just finding the solutions to ax equals 0. Next, we also talked about the column space, which we denote as C of A. So remember, the column space is defined to be the span of the columns of A. But I talked about last time how you can also think of the column space as being the let's see here. Oh, let me phrase it like this. Last time we also talked about how a vector B will be in the column space of A if and only if there exists a solution to the equation ax equals b. Okay. So therefore, you can also think of the column space of a matrix A as representing all vectors b for which ax equals b has a solution. And sometimes that's a more useful way of thinking about the column space. So we've encountered these 2 of the 4 fundamental subspaces. And then the other 2 are the row space. Okay. So the row space, which we denote as R of A for the row space of A. Row space of A is defined to be the column space of A transpose. Okay. Because remember that the rows of A are the columns of A transpose. But essentially, you can think of it as the span of the rows of A. That's essentially what the row space is going to be. And then the last of the 4 fundamental subspaces is, we call it the left null space of A. But it's really the null space of A transpose. Okay. All right. All right. So then we have the null space and the column space of A, and then the row space, which is the column space of A transpose, and also the null space of A transpose. These are what we refer to as the 4 fundamental subspaces of the matrix A. So I'll talk more about them later, but for now, let's maybe start with an example. So let's say we have this matrix A. And for this matrix A, we want to find bases for each of its 4 fundamental subspaces. So we'll go over how to do that with this example. So what you want to do first is you want to start by row reducing your matrix A. So you want to reduce at least to the row echelon form. If you want to reduce all the way to the reduced row echelon form, that's also okay, all right. So let's start doing that with the example that we have here. So I'll start by taking row 2 and adding 2 of row 1 to row 2. I'll also take row 4 and subtract row 1 from it. Okay. Let's work out the rest of the new row 2 and row 4. So when we're doing row 2 plus 2 row 1, we got 1, 1 minus 2, be 1 plus 4, and 4 plus 6. Okay. Okay. And then when we do row 4 minus row 1, 1 minus 0, 0 minus a negative 1, 1 minus 2, and 1 minus 3. Okay. So here's our next pivot in the second column now. So let's take row 3 and minus 2 of row 2. And we'll also do row 4 minus row 2. Okay. So if we do row 3 minus 2 of row 2, we'll get negative 2 plus 2, 0 minus 10, 0 minus 20. And then when we do row 4 minus row 2, we'll get 1 plus 1, negative 1 minus 5, and negative 2 minus 10, so minus 12. Okay. Okay, so in the third column now, we're missing a pivot here, but we can swap rows to move the two up, and then that will give us a pivot now in that third row. So let's go ahead and swap rows 3 and rows 4. So swapping the two of them. Okay. And I'll just do a little bit more row operations, just a few more. Here, let's maybe just to make things nice, let's divide row 3 by 2, and let's divide row 4 by 10. Let's divide this one by -1/10. So I'm making that a +1. All right, good. Okay. And I guess at this point, it looks like I have pivot here, 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 and here. Okay. I wonder if I made a mistake in my row operations. Let me check real quick. Well, that's okay. I might have made a mistake in the row operations, but let's just assume that what I have here at the end is correct. Okay. So this is the row echelon form. So it would be good enough to stop here, but I have a personal preference of reducing all the way to the reduced row echelon form. So I guess just because that's my personal preference, I'll do a few more row operations. So remember, for the reduced row echelon form, you want to get zeros above all of your pivots as well. So I just want to eliminate these entries here, okay? So let me start by eliminating everything here above the third pivot. So I'll do row 2 plus row 3, and I'll do row 1 plus row 3 as well real quick. All right, and then if we do row 2 plus row 3, that's going to be 2 here, 4 here. And then if we do row 1 plus row 3, we're going to get a 3 here and a 5 here. Okay. And then I'm just going to do one more thing, which is I'm going to eliminate these 3 entries. So the entries above the 4th pivot now. So I'll take row 3 plus 3 of row 4, row 2 minus 2 of row 4, and row 1 minus 3 of row 4. So that would put the matrix into this reduced row echelon form now. And then let me just work out the rest of the entries. So row 3 plus 3 row 4 will be -6 plus 6. Here, row 2 minus 2 of row 4, before minus 4 is 0. And then up here, row 1 minus 3 of row 4, that would be 5 minus 6, so it would be negative 1. So here's the RREF. Okay. So I've reduced to echelon form. So now let's start getting bases for each of the fundamental subspaces. I'm going to start with the null space of A. Okay. So the null space is the solutions to AX equals 0. We've already reduced the matrix A. So what I'm going to do now is let's take the matrix that we have here at the end. I'm going to convert it into a system of equations. So the first row gives me 1x1 minus 1x5. And for null space, it's equal to 0 on the right. The second row gives me x2 is 0. Third row gives me x3 is 0. And the fourth row gives me x4 plus 2x5 equals 0. Now, the fifth column is missing a pivot. So I'm going to make the fifth variable x5 the free variable. And the way that I do this part is I assign a parameter to each of the free variables. So I'll make x5 equal to some parameter t. With that, we have x4, moving the 2x5 over. x4 is negative 2x5, so negative 2t. Now here we do have the just x3 is 0 and x2 is 0. And then finally up here, x1 equals x5, meaning x1 would be equal to t, okay? So the solutions to ax equals 0 are going to be all multiples of the vector 1, 0, 0, negative 2, 1. Okay. So this one vector that we got here, the 1, 0, 0, negative 2, 1, this vector by itself would give you a basis for the null space. Okay. Some people will write it in a set, so they put braces around it. I don't think it's too important whether you do that or not. Okay. So here we have one vector in the basis for the null space for this matrix. So kind of as a small side note, you can say the dimension of the null space of A in this example would be equal to 1, okay, since there is one vector in the basis. Okay, so for the column space of A, that one's really easy. So what you do is you just identify which of the columns have pivots in them. And then you take those columns from the original matrix A, and those columns will give you a basis for the column space. Okay. So in this example here, we have pivots in the first 4 columns. So I'm just going to take the first 4 columns of A. So the first column of A was 1, minus 2, 0, 1, etc. So these 4 columns will give you the basis for the column space of A. Okay. And in general, what you do is you just take the columns from A that have the pivots in them, and those will give you the basis for the column space. It's pretty simple. row space is also pretty simple as well. So for the column space, we took the columns that had pivots in them. So for the row space, we want to take the rows that have pivots in them instead. Now there's one small difference, which is for the column space, you have to take the columns from the original matrix. So it would be wrong if for the column space, you took the columns from the row echelon form or the reduced row echelon form. Okay. Now for the row space, however, you can take the rows from the original matrix A, but you can also take the rows from any of the row echelon forms or the reduced row echelon form. Okay. And it's slightly better if you take the rows from one of the row echelon forms rather than the original matrix. So in particular, I'll go to my reduced row echelon form up here. I'll take the rows that have a pivot in them. In this example, that will be all 4 of these rows. So those 4 rows written as a vector. So the first row is 1, 0, 0, 0, minus 1. Second row was 0, 1, 0, 0, 0. So all of the rows that have pivots in them in the reduced form of A, those will be a basis for the row space. Okay. All right. Now, I often get the question, why did I write the rows as columns when I'm writing out the basis for the row space? There's a couple of reasons for that, but maybe the most straightforward reason perhaps is that, remember, the row space is actually the column space of the transpose. So it should be like columns rather than rows. Okay, so that's why I wrote it as columns here. Okay. And now the last of the 4 fundamental subspaces was the null space of A transpose, also known as the left null space of A. So this one's always the harder one of the 4, okay? So the first 3, we were able to find a basis for each of them, essentially using the reduced row echelon form. For this last one, the left null space of A, you cannot get a basis from it by looking at the RREF, okay? So let's say the REF does not give much info about the left null space. It gives some, but not enough to get a basis for it. Okay. So we have to do a little bit more work to get a basis for this last one. So here's my sort of recommendation for how to get a basis for the left null space of A. So what I recommend doing is get your basis for the column space and take those vectors and put them into a new matrix as rows. So I'm going to take the 4 vectors in the column space in this example. And here, as I said, I'm putting them into a new matrix, but as rows this time. So it's kind of like transposing the matrix since we're looking for the null space of the transpose. So we get this new matrix, and then now you're just going to find the null space of the new matrix. And the null space of this new matrix is going to turn out to be equal to the null space of a transpose, and that's why we're doing this step now, okay? So to find the null space of this new matrix, we would actually have to go through the row operations again and put it into at least row echelon form or reduced row echelon form. Here, let me go ahead and save some time by not doing all the row operations. So I'm just going to cut to the end result. Whoops. So assuming that I did my row operations correctly, then for this example, like earlier, assuming I made no mistakes up here, although I fear that I maybe did at some point, okay? But let's assume that I did make no mistakes. So we found that these four vectors are linearly independent. And that's why they gave you a basis for the column space. So since these four rows are independent, you should end up with 4 pivots. So therefore, the reducible echelon form should look like this, okay? Otherwise, so just like in general, you need to do the row operations, okay? But in this case, this would be the REF, and then what does that tell you about the solutions for the null space? Well, the first row will just give you one equation, x1 is 0. Second row gives you an equation, x2 is 0. Third row gives you x3 is 0. Fourth row gives you x4 is 0. So the null space of this matrix, which is the null space of A transpose, will consist only of the 0 vector. This was the only solution. Okay. So when this happens, and this happens occasionally, I think it happened in one of your homework problems this time as well. So if your null space, or if your null space of the transpose, if it is just the 0 vector, then a basis for the space would be an empty set, which you can denote as a set with nothing in it, the way that I did here. Or you can also denote the empty set usually like this. So it's like a circle or a 0 sort of with a line through it. This is kind of a very special case. But if one of your spaces consists only of the 0 vector, then a basis for that space would be an empty set. Okay, so there would be nothing in the basis. By the way, since there's 0 vectors in the basis, that would imply that the dimension of this space would be equal to 0 since there are 0 vectors in the basis. Okay. And then I guess just kind of as a note for up here, we had 4 vectors in the basis for the column space and the row space. So the dimension of each of them would be equal to 4. All right. So now let me just mention a few facts about the 4 fundamental subspaces. So first I want to talk a little bit more about the dimensions of each of them. So the dimension of the column space and the dimension of the row space, these are always the same. And if you think about how you get a basis for these two spaces, column space and row space, they come from the columns with pivots and the rows with pivots. So their dimension is going to be equal to the number of pivots in your matrix. And then if you remember the number of pivots in A, we defined that previously to be the rank of A. So the dimension of the column space and the dimension of the row space, those are both going to be equal to the rank of the matrix. Okay. Regarding the null space, okay. So for the null space, if we go back to the example that we just did, here we ended up with one vector in the basis for the null space, and that's why the dimension was equal to 1. Now you have one vector in the basis because you had one free variable. So in general, the dimension of the null space will equal the number of free variables that you have. And remember that you get one free variable for each column without a pivot. So you can also say the dimension of the null space is the number of columns without pivots or without a pivot. Okay. Here as the very small aside, the dimension of the null space, some people refer to that as the nullity of A. I don't think your class uses that terminology, but I guess it's worth mentioning. So sometimes people refer to the dimension of the null space as the nullity. Now, the dimension of the column space, which was also the rank, that's the number of pivots in A. You can also think of it as the number of columns with pivots. Okay. All right, so we know dimension of the column space is the number of columns with pivots. And then we know that dimension of the null space is the number of columns without pivots. So if you add these two numbers together, that should just equal the total number of columns in your matrix. So if A is an m by n matrix, then it would have n columns. So you'd have that the dimension of its column space plus the dimension of its null space should be equal to n. So this formula is sometimes referred to as the rank nullity theorem. Since the dimension of the column space is the rank, and as I just mentioned, the dimension of the null space is the nullity. And we're saying those two always add up to be equal to n, the number of columns of A. There's also a similar equation. If I just replace A with A transpose, then column space of A transpose would be the row space of A. And then instead of null space of A, you'd have the left null space of A now. And these would total the number of columns of the transpose, which would be the number of rows of A, which would be m if it were m by n, okay? So we have this fact as well. Okay. And then aside from these facts, I also want to mention something about the orthogonality between these four fundamental subspaces. So let's think about the row space and the null space of a matrix for the moment, okay? So let's say that I have a matrix A. So it has some number of rows, so row 1, row 2, etc. So let's imagine these are like the rows of the matrix. And I'm thinking about the row space and the null space. So let's imagine that we have AX equal to 0. So that X is a vector in the null space, okay? And therefore AX equals 0. Now, if you think about when you do matrix vector multiplication, remember that matrix vector multiplication involves doing dot products, where you do the dot product of row 1 of A with vector X, and that would be equal to 0. And then here, like row 2 dot product with X would again be equal to 0, since X is in the null space, so the right-hand side is all zeros. So the dot products of all the rows of A with X is 0. And remember that when the dot product of two vectors is 0, that means that the two vectors are orthogonal to each other. So here we get this, we have this kind of observation that the rows of A are orthogonal to X, where X was a vector in the null space. And so because of this, we have this kind of relation that the vectors in the row space of A are orthogonal to the vectors in the null space, okay? So roughly speaking, so essentially you can say that the row space of A is orthogonal to the null space of A. And then just similarly, if you just like replace A with A transpose, I guess row space of A transpose would be the column space of A. And these two satisfy a similar relation that the column space of A is orthogonal to the left null space of A, meaning that all the vectors in the column space will be orthogonal to all the vectors in the left null space, okay? So these relations are pretty important. The second one here in particular, the column space and left null space are orthogonal. That comes into play when we start talking about projections, so keep that one in mind in particular. And I'm a little bit over time, but I'm going to just maybe squeeze in a few quick examples to end this review. So there were some questions in your homework assignment where they asked you to find a matrix satisfying certain conditions or to show that such a matrix does not exist. I wanted to take a look at just a few of them and just kind of maybe highlight some things that you might be looking for in order to try to answer those questions. Okay. So maybe look at maybe two examples or something, okay? So let's say for the first example of this type, let's say that we want a matrix A such that the basis for its column space consists of the vectors 1, 2, 3, 2, and negative 2, 1, 3, 0. And then let's say that the basis for the null space of A should be 0, 3, 1. Okay. So can we find a matrix satisfying these two properties, or if not, we need to show that such a matrix cannot exist. All right, so let's think about this for the moment. So because there are two vectors in the column space, that means the rank of this matrix would have to be equal to 2. So it would have to have exactly 2 pivots, no more and no less. And then here, the basis for the null space is just this one vector. So that means the null space is one-dimensional, which means you should have exactly one free variable. Or if you will, you should have one column without any pivots, okay? Okay, so let's think for this matrix. Now, we also had one more fact. Well, I guess it's not too important. Okay, I don't need to mention that. Well, I'll mention it anyways because it's maybe nice to use one of the facts that we talked about earlier. So we also talked about how we had this rank nullity theorem where the rank of the matrix plus the nullity equals the total number of columns of the matrix. So in this example, the rank is 2. The nullity, or the number of columns without pivots, is 1. So 2 plus 1 gives us 3. So this matrix A must have 3 columns, okay? So let's try to set up an example. Okay. Now, for this matrix, for these two vectors to be in the column space, the most natural thing to do is to make these vectors 2 of the columns of A then, okay? Now we know that the matrix must have a third column, but I don't know what this third column should be just yet either, so I'm just gonna fill in some variables for that. And then lastly, I need this one vector to be in the null space. So that means A times this vector must be equal to 0. All right, so then if I do the multiplication real quick, you'll get 0 minus 6 plus A. You'll get 0 plus 3 plus B. 0 plus 9 plus C. And 0 plus 0 plus D. So that needs to be equal to 0. So therefore, you get that A would have to be positive 6. B would have to be negative 3. C would have to be negative 9. And D would have to be 0. Okay. So that means if I choose matrix A to be this matrix here, A is 6, B is negative 3, C is negative 9, and D is 0. This matrix A should satisfy the given conditions, okay? Its column space will be these two vectors since we placed them into the matrix as columns. This vector is in the null space because we set up the third column to make that happen, okay? All right, so here we came up with a matrix that satisfies the given conditions then, okay? I don't want to go too much over time, so I'll just end with kind of one more example. So let's say we now want a matrix that has as a basis for its row space. Let's say maybe these two vectors here. And then maybe as a basis for the null space. Maybe let's just say it's this one vector here. Okay. Okay, now here, when they give us information about the row space and the null space. So if we look to the orthogonality relations that I mentioned earlier, row space and null space are supposed to be orthogonal to each other. Okay. Okay, however, so that means like this vector that should be in the null space should be orthogonal to these two vectors in the row space. So we can check if that works or not. So if I take vector 2, 3, negative 1, 1, and if I do the dot product with 1, 0, 2, 0, in this case, you get 2 plus 0 minus 2 plus 0. So it actually equals 0. So these two vectors are orthogonal, as they should be if they were in the null space and row space. Now this vector should also be orthogonal to this one as well. You can check if the dot product is 0 then. And in this case, when we do the dot product, it's negative 6 plus 3 plus 0 plus 2. So that's going to be -1, which is not equal to 0. So that means that these two vectors are not orthogonal to each other, since their dot product is not 0. And that proves that such a matrix A cannot exist. So maybe let's write out this. So no matrix A satisfying these conditions exists, since the null space and the row space have to be orthogonal to each other. Okay. But in this example, we saw that they were not orthogonal. Okay. All right, so I'll end my review with that.